The modern wireless spectrum is a densely packed environment. Thousands of invisible data signals overlap in the space around us constantly, creating a high-density sea of electromagnetic energy. A primary requirement for any wireless receiver is the ability to distinguish its intended signal from the interference generated by neighboring bands. To achieve this isolation, engineers rely on four foundational filter architectures: low-pass, high-pass, bandpass, and band reject. Low-pass filters attenuate high-frequency noise, which is a standard step for anti-aliasing in analog to digital converters. High-pass filters perform the opposite role, blocking DC offsets and low-frequency interference. Bandpass filters allow a specific spectrum to pass through, effectively selecting a target communication channel. When the problem is a narrow source of noise, like a 60 Hz power line, band reject or notch filters are used to eliminate that specific frequency. Mastering these four architectures provides the necessary foundation for maintaining signal integrity at the physical layer. In pure theory, these filters operate flawlessly. As shown in these diagrams, they are modeled as brick walls that cut off unwanted frequencies instantly at a specific threshold. But physical hardware cannot achieve this instantaneous drop-off. Looking at the dashed actual line in this graph, we see the reality: a gradual, sloped transition band. The steepness of this physical curve, the roll-off rate, is determined by the filter's order. A higher order circuit creates a steeper slope, but requires more complex components. Because physical filters are inherently imperfect, engineers use specific mathematical models to approximate the ideal brick wall as closely as the application requires. Filter design is an exercise in compromise, choosing exactly which mathematical trade-offs a system can tolerate. To manage these compromises, we use the S-domain. Here, we define a filter's behavior through a transfer function. On this 3D surface, poles pull the response upward into peaks, while zeros push the response down into nulls. Shifting the placement of these poles determines both the stability of the circuit and the exact shape of its frequency response. This creates a mathematical trilemma. It is impossible to simultaneously achieve maximum passband flatness, perfect phase linearity, and a vertical roll-off. This is the Butterworth approximation. It provides a perfectly flat passband, but you can see that it has a relatively slow, sweeping roll-off into the stopband. Engineers choose the Butterworth model when the highest priority is passing a signal without any amplitude distortion. If the system needs higher selectivity, we use the Chebyshev approximation. The roll-off is much steeper, but it introduces ripples across the passband. In this model, we trade amplitude accuracy for a faster transition to the stopband. For the maximum possible selectivity, we use the elliptic or Cauer approximation. It provides a nearly vertical transition, but with aggressive ripples in both the passband and stopband. These filters come with significant costs, specifically extreme transient ringing and very poor phase linearity. The constraints of S-domain mathematics force engineers to pick the approximation that best fits the specific tolerances of the signal being processed. Moving from math to physical hardware, the implementation strategy is dictated almost entirely by the operating frequency. At lower frequencies, traditional passive networks relied on heavy magnetic inductors to achieve these curves. Modern low-frequency designs utilize active filter networks. These use operational amplifiers, or op-amps, shown here as the central triangle, to shape the signal. The advantage here is that op-amps allow us to replace bulky inductors with compact resistor and capacitor networks. These active circuits also provide signal amplification, or gain, which a passive filter cannot offer. Additionally, op-amps provide high input and low output impedance, isolating different circuit stages to prevent loading effects. This active approach allowed engineers to integrate complex filtering math directly onto lightweight microchips. However, at microwave and 5G frequencies, active op-amp filters hit their bandwidth limits and fail to operate. For these high frequencies, we shift from moving electrons to moving physical sound waves through a solid medium. Surface acoustic wave, or SAW filters, use transducers to convert electrical energy into acoustic waves on a piezoelectric substrate. While SAW filters are common in mobile devices, they struggle with performance and efficiency at frequencies above 3 GHz. To support the 5G NR bands, we rely on bulk acoustic wave, or BAW filters. BAW devices propagate the wave through the bulk of the material rather than across its surface. This results in lower insertion loss and superior thermal stability at higher frequencies. To maintain selectivity at gigahertz speeds, the architecture must transition from electronic circuits to mechanical acoustic resonators. We see these technologies combined in one of the most demanding RF environments, a communication satellite. A satellite transponder must manage hundreds of high-power, overlapping signals without causing interference between channels. The input multiplexer, or IMUX, handles the uplink. It separates a dense composite signal into isolated individual channels. The IMUX uses high-selectivity band-pass filters, often based on Chebyshev or elliptic models, to pack these channels as tightly as possible. The output multiplexer, or OMUX, performs the opposite task, combining amplified signals for the downlink back to Earth. Because it handles massive transmission power, the OMUX prioritizes low insertion loss filters to manage heat, even if it means sacrificing some roll-off steepness. Satellite communication depends on this careful pairing of mathematical approximations with specialized physical hardware. The engineering of frequency-selective circuits spans from mapping abstract poles and zeros to carving acoustic resonators in piezoelectric materials. There is no single perfect filter design, only specific compromises tailored to the needs of a particular signal. While the mathematics define the shape of the response, the frequency requirements dictate whether it is built using op-amps, SAW, or BAW devices. This selective architecture is a fundamental requirement for the function of modern global telecommunications. These systems ensure that a specific transmission can be isolated and processed even as the spectrum becomes more crowded. The precision of these frequency-selective networks is what allows our high-bandwidth infrastructure to remain functional as more devices and data rates are added to the environment.